Hello, welcome to our next webinar. My name is Kendra Spires. I'm part of the Envent technical sales team here in Canada. Today we're talking about our Tunable Filter Spectrometer, our TFS. We've got Bob Johnson, our very own CEO, who's actually going to walk us through what a TFS is, how does the TFS work, how to calibrate it, some benefits of the TFS, considerations when using a TFS, as well as some applications that you can use the TFS for. We also have quite a few different common questions that our users and customers have asked, so we're going to go through that as well. Envent is a Canadian manufacturing company. We manufacture our own analyzers here in-house in Calgary. We have our M series, our M60, 70, and 90, our oxygen, H2O, and carbon dioxide analyzers. We also have our 330S and 331S H2S analyzers, which is our Class 1 Div 1 and our Class 1 Div 2. We have our portable H2S analyzer, our sulfur sentry as well. On top of all that, we also have our gas chromatograph. So we've got our 131, which is a Class 1 Div 1, and our 132, which is our Class 1 Div 2. We at Envent are also reps for Michelle Instruments. So we are able to provide some water content and hydrocarbon dew point and water dew point analyzers, as well as their oxygen analyzers and many other options. We're going to talk about our Tunable Filter Spectrometer, which is one of our other offerings here at Envent, as well as we will build the sample conditioning systems for these analyzers for your application specifically. Along with all that, we have our buildings, enclosures, and probe assemblies, and we are essentially a one-stop shop. We'll provide the entire solution for your application. So let's get started. We're actually going to be talking about our TFS, which is great for high concentration H2S solutions. H2S, as you know, is about 1/3 of our natural gas here in Alberta contains H2S. It's colorless, heavier than air, and extremely toxic. In low concentrations, it smells like rotten egg and causes throat and eye irritation, but in high concentrations can be deadly. H2S is one of the most corrosive components in gas, water, air environments, so we want to make sure that you have none or you can deal with that H2S properly. Thanks for joining us today. I'm going to pass it on over to Bob, and he's going to take away the TFS.
Thank you, Kendra, for that wonderful introduction. My name is Bob Johnson, and I'm going to be spending the next 20 to 25 minutes with you guys doing a presentation on the TFS, or Tunable Filter Spectrometer. This presentation is really meant as a basic outline or introduction to the analyzer and some of its capabilities, and an opportunity to make you guys at least aware of technology that may be available to you for certain applications. So basically, the TFS is an all-optical approach to multi-component analysis of hydrocarbons and other infrared detectable components. So as a gas chromatograph that you may be familiar with would use a TCD detector as an example and separate out and measure methane, ethane, propane, butane, and so on, the TFS can also isolate specific components and give multiple component analysis from one hydrocarbon stream. So here is a couple of pictures of the actual optical bench. And as you can see, if you look at the bottom picture of the optical bench, you'll see an infrared light source. That is a broadband infrared light source that emits light over the full spectrum. I have an actual sensor here, and this is actually what a sensor looks like. And all it is basically an infrared a light bulb, or a tungsten bulb that is easily replaced. Okay? So in addition, if you look at the cell on the top picture, you'll see that there is a sample inlet and a sample outlet in the middle of the sensor that allows a sample to continuously flow through the sample cell. And that there is a filter, or what's called a Fabry-Perot interferometer. You can see it at the rotating filter on the top picture, or also on the bottom. That basically rotates at about approximately 300 RPM. And if you look a little bit closer on the next slide that I'll show you, you'll see that that filter isolates the full hydrocarbon stream into two specific wavelengths. And those are the two wavelengths where the components that we want to measure will absorb light. Okay? In addition, the sensor is pressure compensated, so we can compensate up to 30 psig. So if you have back pressure on your sample, or if you want to put that to flare, you can do that, because it will compensate for the pressure changes that happen within the cell. In addition, we hold the cell constant at 60 degrees C. Because there can be an influence in temperature as it changes, we keep it always constant at 60 degrees C. So here is another video that I'm showing you, and you can see in a better format the actual two filters, which are red and blue. The mirror in front, which is the yellow piece that you see there, it deflects through that filter and isolates those two wavelengths where we want to see light absorption happen. Okay, so how does the TFS work? Well, basically the sensor provides a continuous wavelength sweep within a narrow target wavelength. So as I showed you before, you can see on the two columns there is one area of light absorbance where the hydrocarbons reside, and there is one area where the CO2 and H2S reside, okay? So we do an actual sweep using that rotating filter that takes a look at the light absorption of all those different components. The problem is, and this has always been a bit of a quandary as far as infrared analyzers go, is that, for example, on the hydrocarbon stream, you can see that a lot of the absorption curves are overlapping. And so it was very hard to identify which was which and how big the curve was, because basically we're measuring the area under the curve to determine the amount of gas that is actually present in the stream, okay? So what we do is not only isolate those two specific wavelengths, we can see all those multiple hydrocarbon absorption curves, but what they do is something called modeling, or using, in a fancy word, a modified partial least squares polynomial regression. I know that's a big word, but for spectroscopists they would be fairly familiar with that. Okay. So how does this work? Basically, there are two ways that we do this. First of all, the analyzer is permanently characterized at the factory. Now you'll see in the picture on the top here, C1, C2, C3. We actually send the sensor to school, or teach it what methane looks like in a full hydrocarbon stream. So they'll run methane through, they'll identify the absorption curves where the measurement occurs, and then they'll store them in a library. And then what they'll do is they'll run ethane, and they will start to identify those absorption curves and store them in the library. And they continue on for all the different components that they would like to measure. Okay? Now, the sensor also has in the field the capacity to run a validation screen, or a validation procedure, which you can use just with calibration gas, and it also gives you the opportunity to do a auto zero with instrument air or nitrogen. But the analyzer itself is permanently characterized and does not need an actual calibration once it reaches the field. Okay. So we see that you have your sensor that's located with the light that's emitting in and doing the absorption. You see that we're isolating the two different wavelengths where the light absorption occurs. And you'll see also that all the different absorption curves are over top of each other. But since we have characterized the sensor, the analyzer keeps looking at each of those peaks, and it can identify each one individually by using the algorithm or by using the modeling to determine what the actual area is on the absorption curve for each of the components. And as a result, we get actual isolated measurements of, an example, methane, ethane, propane, normal butane, isobutane, and so forth. Okay, so the end result is that we have a TFS sensor that provides some of the following. First of all, it has a very high linear and repeatable multi-component hydrocarbon analysis. So you can see that I've given examples on the right-hand side of all the different components that the analyzer can measure that we would use it for. So methane, ethane, propane, isobutane, all the normal butanes, ipentanes, CO2, and H2S. In addition, ranges vary and they can be changed, but our standard one would be from 0 to 100% and percent level measurements. As far as accuracy, we're looking at an estimated accuracy of plus or minus 0.3% or 0.3 mole percent, or plus 1% of full scale. And with regard to repeatability, is quite amazing at less than 0.1 mole percent. Okay? In addition, the sensor is compensated for water in the sample up to 3%. And also, the sensor has over 30 different what they call recipes available. So we can actually also do measurements like ethylene or propylene, trace levels of CO, so on and so forth. But the most common measurement or recipe that we use is the 253. The two designated that there are two filters that we use that you saw before that were rotating, where they isolate the wavelengths of absorption that we're most interested in for the measurement. In addition, we also can provide a BTU analysis or also a Wobbe index analysis. Okay, some of the specs for the analyzer. First of all, with the 253 measurement, which we most commonly use, we're doing measurements from C1 to NC6, CO2, and H2S. The analyzer itself comes in CSA approved for Class 1 Zone 1 or Zone 2. We can also do 24-volt power supply or 120 volts AC. There is a 4-line display on it. You get two 4 to 20 milliamp outputs. You have the ability to do RS-45 via serial Modbus. And we also have Ethernet Modbus TCP. The configuration software is included with the analyzer. There's an alarm and event logger. And of course, with every analyzer, it also requires some kind of a sample conditioning system and probe that we will design specifically to your application. So some of the benefits from a TFS is, okay, first of all, we have the ability, as I've mentioned before, with the sensor being pressure compensated at 30 psi, so any kind of pressure fluctuations or measurements or in the measurement will not be influenced by pressure changes. There's also a simplicity to the analyzer. Basically, the sample is coming in and it's going out. There are no valves, there are no columns, there's less technical training as far as maintaining or supporting the analyzer from a maintenance perspective. There's also less utilities required. So as an example, we don't require carrier gas. There's no instrument air required except for actually zeroing the analyzer when you first start it up. Certainly there's also, obviously, as a result, a reduced cost of ownership based on all the other components that may be required to run the analyzer. It typically comes in a smaller footprint, so it's much smaller and easier to put into usually what are crowded analyzer houses or other areas. And you can also run with a longer unattended operation of the analyzer. Okay. So things to consider when you're looking at purchasing or acquiring a TFS. First of all, we cannot presently provide the same number of speciated components that, as an example, a GC could provide. So we can't do a C6 plus or C7 plus, C8s. Also, we can't see any of the diatomics. So when I refer to those as inerts, I'm talking about things like we can't see hydrogen, oxygen, nitrogen. I think the other ones are chlorine, bromine, and there may be a couple of others. The sensor is simply blind to those measurements. It's also always important to provide an application data sheet when you're looking at using these analyzers. We need to understand your application, what you're trying to achieve, and what is in the background of the gas that you're measuring to ensure that the analyzer is a good fit for what you're trying to do. The analyzer does require a periodic zero, again, as I mentioned before, with regard to nitrogen or with regard to instrument air, and I would say approximately every 3 months or so you could do that. I'll remind you that the sensor is permanently characterized. That means that there is no calibration required once it leaves the factory. However, we can do some small span adjustments, and we can also verify that the analyzer is running correctly by running verification gas. Okay? The light source that I showed you before is a replaceable item. Pay Basically, it's approximately every 18 to 20 months, but we've had a number of units that have run for longer than that without any replacement at all. And again, very important to remember, like any analyzer, it requires a customized sample system that provides a clean and dry representative sample for the analyzer to measure. So always critical, sample conditioning system must go with the analyzer. Okay. Some of the applications that we've used that I'm just going to quickly go through for you. Examples like acid gas reinjection, where we're measuring H2S and CO2. BTU Wobbe index for SAG-D applications on steam gens. Railcar loading, flare gas, plant inlet, LPG pipelines, pipeline blending applications for measuring H2S. And we're open to other applications and different recipes that we can use for the analyzer. So first, I wanted to talk about acid gas reinjection, a very common application for us for measuring high-range H2S as well as CO2. In addition, this particular analyzer was measuring on the inlet to a Klaus plant after the amine treater, where we have high concentrations of H2S up to 60 or 70%, and then the remainder of that being CO2. Another very common application that we found that has been very helpful and very applicable for this analyzer is BTU or Wobbe index, in particular on SAG-D steam gens. So basically what you have is a sample that's coming in that's expensive as far as natural gas feed for these steam gens. So in some instances, end users are using poor quality gas. It may have higher concentrations of CO2 and that sort of thing, but there's an issue with regard to maintaining a certain BTU level in order to prevent flameouts or other safety related issues and also complete combustion. So the advantage on this analyzer is that we can provide an analysis for Wobbe index measurement as quickly as 1 to 2 seconds for the analyzer. In the applications where we were using, we only had 12 seconds to respond. So from the point the sample left the sensor until it was analyzed, we were able to do under 12 seconds. And what the analyzer was able to do was either monitor or could control fuel gas injection to the steam gen in case the BTU or Wobbe index quality was not good enough to support the proper combustion. So certainly from a process application, this is a great analyzer to consider for its speed. Now as far as BTU analysis goes, we're not a cash register. We're not a GC that's going to give you plus or minus 0.25 of BTU. But what we can give you is 10 to 15 BTU analysis as far as accuracy goes, but in a much faster response time. And so in certain applications, that's more than good enough. Railcar loading is another application that we've come across that's been quite successful. So in certain instances where rail cars are coming in, as they are filling up their rail cars with different hydrocarbon liquids, there is an output of the gas that already exists in the rail car that goes to an incinerator. And again, Wobbe index or BTU analysis provides an opportunity where if you've got a lot of air that's going through of the vent of the rail car, we can do that fuel gas injection and provide that control so that we're not flaming out, or so that you're not getting poor combustion with a lot of black smoke that's coming up. So it is a control or process analyzer for those type of applications also. Another application where we had very good luck was on flare gas. And this was for a gas storage facility in northern Alberta, and we had 2 of these analyzers monitoring flare gas. Basically, again, Wobbe index or BTU analysis, and what they were using was, depending on what gas they were providing to the customer, they would have different components that were going through the flare. And they needed to have control of their air fan that provided or ensured that they had proper combustion as it was going up the flare. And this analyzer, being able to be fast enough and to take enough of the components to give them a decent BTU value, allowed them to allow complete combustion going up the flare. This was another application which was for plant inlet. I think there were 3 streams that were going through. One was, I think, a acid gas stream actually for H2S and CO2, and then we had 2 sour streams coming in with higher ranges of CO2 or H2S, sorry, I believe at percent level, as well as a C1 to C6 plus analysis. Okay. A few very common questions that people ask that I answer, and again, feel free to ask any questions you want on the chat part of your video interface. But what happens if the sensor gets dirty? Okay, so basically, the internal components of the sensor, the mirror, the detector, the filter, can tolerate some contamination, and the sensor has an alarm if the IR source gets too weak to complete the measurement. So a key thing to remember is we can, as long as we can see the beam by the light detector, then we're usually good to go with continuing to provide a consistent measurement. And what you're seeing is, the graph I've provided, is that the green line that goes down is actually showing the light source decreasing as low as 50%, but the components that are being measured are not influenced even when we see that drop in light source intensity. Okay, what happens if an unanticipated component shows up in my stream composition? So here's the bottom line. The analyzer anticipates what the gas stream is and is calibrated at the factory and characterized. So if you provide a gas stream for us where there are some components that we don't anticipate, the possibility exists that it will absorb some of that components and then cause some crossover or contamination with the other streams. In most of the applications that we're doing, we are seeing consistent components that would be appropriate, so we're not seeing other components that would influence. However, I can think of one example where we had methanol, and it was at percent level, and it was interfering with the measurement of H2S and CO2. The methanol was at percent levels. So what we were able to do is actually characterize the sensor with methanol over a remote access through to the factory, so they actually could measure the percent levels of methanol and compensate for them. This is why it's so important that when you're considering this kind of technology, that we get a good background gas of what's expected and the components that you want to measure. Another question is, does the TFS have Measurement Canada? The answer is not at this time, and typically we would never see that. This is more of a process analyzer and not going down to the levels that you require in order to achieve that Measurement Canada certification. Okay? Is the sensor easy to clean? Well, here's an example of taking the sensor apart. You'll actually see with the sensor that there are a number of squiggly lines, and what that allows to do is the sample is actually going through that tortuous path and heating up before it actually goes into the cell to be measured. So we have kind of timed our technicians, even on the first few times that I tried to clean it. We can walk 3 people through it. Sometimes you may only have to take the mirrors off and clean them off. Sometimes you may have to take the whole sensor apart. But we have had ones that have been filled with liquid. It's about a 2-hour process. You take it apart, you clean it, you go up and you start running again. Okay, another question, why do you lump the NC4s, NC5s, and NC6? So I don't know if you had noted that earlier on the presentation, but the normal butanes, the NC5s and NC6 are so close, overlapping each other, that we can't see or isolate one from the other. So what we do is we record all 4 of those, or 3 of those butanes as one lump sum, and they're reported as the NC4. So for certain applications where you want to speciate NC4 and NC5, this may not be as right an application for what you're, or analyzer for what you're looking for. Another question that comes up, what range of H2S can you measure? Well, we can do anywhere from 1% up to 70 or 80% H2S. Again, in most applications you'd be doing that kind of measurement would be for acid gas. Anything below 1%, because of the absorption strength of H2S with infrared light, is not that great, so we don't recommend going below more than 1%. Another question that gets asked is, can we measure liquids? Well, a TFS always measures in gas phase. But that being said, if we do have some liquid samples that when we heat up to 60 degrees are in a gas phase, then we can do the measurement. So you could have a liquid sample under high pressure in the process, but when it's extracted and vaporized, we still may be able to do the measurement. Okay, so there is a very quick introduction to the TFS. If there are any additional questions or of interest, things that you would like to talk about, please don't hesitate to give our office a call. Please stay tuned as we promote other upcoming sessions for new products. And please complete the survey of what's provided and tell us what you'd like to learn about next. Thanks again for your time, and have a great day.